Welcome back for your next flipped classroom video. Thank you for joining me. Again, a quick reminder, please make sure you have your packet in front of you, something to write with in front of you, and your calculator in front of you. So to begin this lesson, we're going to be talking about scientific notation. We're going to do a really quick review of what we did in lesson 7.1, where we were just dealing with exponents. So this first question, simplify negative 23xyz to the 0. Now, hopefully you recall, anything to the 0 power is going to be 0. Now, this only applies to what the 0 is actually influencing. So here, that 0 exponent is influencing the parenthesis. So this entire parenthesis becomes 1. But we have that negative out front that is not a part of the parenthesis. So this whole thing actually becomes -1 for us. Looking at our next one, this one looks like a beast. But really all we have to do is make sure that we're putting everything in its proper place. So I view it easiest to do this by working one variable at a time. So I'm going to start going across the top. That 2 does not have a negative exponent, so it's happy where it is. M squared does not have a negative exponent, so it is also happy where it is. Then n to the -3, it does have a negative exponent. It is not happy where it is. We have to take that n to the -3 and move it to the bottom. P to the 0, well, there we're talking about 1. Anything to the 0 power is 1, so really we're multiplying by 1. All right, next, let's do that same process along the bottom. So that 8 does not have a negative exponent, so it just stays on the bottom. Q to the -5 does have a negative exponent, so we have to move it. So Q to the 5 up on top. Then -2 squared. The difference between a number being negative and having a negative exponent. Okay, so it does not have a negative exponent. It does not have to move, but we can write that better. -2 squared simply gives us 4. So now that we have all those negative exponents taken care of, let's write everything a little bit nicer, shall we? So we have 2 times 1 on top. So that's going to give us 2m squared q to the 5. And, I'm sorry, this should be a +3, not a -3, so ignore that negative I had originally written. So, on the bottom, we have 8 times 4, which is 32, and then n cubed. So we're just simplifying, writing everything a little bit nicer. Now, reducing fractions, 2 over 32. That is the same as 1 over 16. So that's how I'm going to write this. And that is going to be your fully simplified answer. Okay? And again, we'll get more and more practice on that because I realize that's a little bit of a long process, but I promise you, you will be able to do that. Now, for today, we're talking about scientific notation. So our intro, determine how many times your heart beats in 100 years if it averages 80 beats per minute. Okay, so just quickly running through this, the idea is I want you to see how large of a number you're going to get. So 80 beats per minute, multiply that by 60 to get how many beats in an hour. Multiply that number by 24 to figure out how many in a day. Multiply that by 365 to see how many heartbeats in a year. In 100 years, you have to multiply that by 100. So just to give you a quick look at what that looks like, the number we are talking about is that. Huge, huge number. So the idea is, scientific notation says, there's an easier way to write numbers when we're getting that large, okay? Because that number really doesn't mean much to us. So, what is scientific notation? I'm hoping you've seen this in science class, okay? what scientific notation is. An example, you take a number. Now that number has to be between 1 and 10, all right? So you have a number multiplied by 10 to some whole number exponent, okay, some integer exponent. So that is scientific notation. So it's always a number between 1 and 10 times 10 to some integer. Right? That is scientific notation. So, keeping that in mind, let's look at these first couple. All we need to determine is why are they not in scientific notation. So, looking at that first one, 0.98 times 10 to the 8. The problem that I see there is this. 0.98, that number out front, that is not between 1 and 10. So, in this case, that is why that first one is not scientific notation. That number needs to be between 1 and 10. For the next one, 1.4 times 10 to the 1/2. So this time the problem I'm seeing is right there. The exponent has to be an integer. So in this case, that one is not an integer, therefore that is not considered scientific notation. And for the third one, 4.5 to the 10th power. Well, our problem there is, where's the multiplying by 10? Okay, I don't see anywhere where you're multiplying by 10 to some exponent. So that is why that one is, again, not scientific notation. Okay, so there's a brief little overview about what scientific notation should look like. Identifying is something actually in scientific notation or not. So, the real question, how do we go in between scientific notation and standard form? So, that first one, 3,402,000. So, what we need to do is, for a number like this, we need to start with our decimal point. We need to move that decimal point until we get our number to be between 1 and 10. All right, so that's always our goal. So let's see here. So I need to move my decimal over. 1, 2, 3, 4, 5, 6 spots. When I move it over 6 spots, I now have a number between 1 and 10. I have 3.402. Okay, so I've achieved my number between 1 and 10. I moved my decimal over. Times 10, well now I moved my decimal 6 places, so that is going to be the exponent that the 10 gets. I moved it 6 spaces, so times 10 to the 6th. Alright? So, let's take a look at it the other direction, okay? So here, for 0.000045, our goal is still the same. We're looking to get it between 1 and 10. So let's move our decimal. 1, 2, 3, 4, 5, 6. All right, so I moved it over 6 spots. When I stop in between the 4 and 5, that gives me a number between 1 and 10. All right, now, something you may have noticed. This time, we started with a decimal, okay? We started with a number less than 1. So when we're moving in that direction, we're dealing with a decimal number, something smaller than 1. We moved 6 spaces, but we moved 6 spaces in the opposite direction. We moved it in order to make the number smaller. So this time, it's not 10 to the 6, it's 10 to the negative 6, because we were dealing with a number less than 1 to begin with. So when you're dealing with a number greater than 1, you get a positive exponent. When you're dealing with a number less than 1, you're dealing with a negative exponent, a negative movement in that decimal place. But you're always counting how many times did I move my decimal. All right, now it's also a skill being able to go backwards. Okay, so if I give you something in scientific notation, I expect you can put it back in standard form. So here we have 2.03 times 10 to the 6. So we're starting with 2.03. Now that times 10 to the 6 means we are moving our decimal 6 spaces. Now, it is a positive 6, so we are moving our decimal 6 in a positive direction. So 1, 2, 3, 4, 5, 6. So that's where our decimal ends. Now notice as I was shifting over, we have some empty spots. In every one of those empty spots that you get when you move the decimal, you can fill those in with zeros. All right. So our final answer in standard form is going to be 203 and then 4 zeros at the end. And that is going to be the standard form of that number. Are we looking at our next one? Again, our starting point is 4.506. And now, times 10 to the negative 10. So again, this time notice our exponent is negative. So this time when we're shifting it over to create the standard form, we're going to be shifting it in the negative direction. So now I'm actually going to rewrite this because I'm going to need a little bit more space. I'm going to write it over here, 506. So I'm going to move it over 10 in the negative direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And for every one of those empty spots, I'm going to put a 0. So to write it nicely in standard form, what I'm seeing is I have my decimal, I have 9 zeros, and then the 4506. So again, hopefully you're starting to see here why we use scientific notation. Because that number is not very helpful to see. It's not really doing anything for us. All right? So now, I'm going to leave it up to you to create your own examples. So after you're done watching this video, I'd like you to go and actually try making your own examples for me. Now, in terms of that important note, the lead number must be, remember, it must be between 1 and 10. Right? That's always a goal. That's what we're looking for. Now, there's another little catch. Notice the next example. 45.6 times 10 to the 7. It wants us to write that in scientific notation. Now, I want you to notice that is not a scientific notation yet, okay? That first number, 45.6, is not between 1 and 10. To get it between 1 and 10, we actually need to move our decimal over again, okay? That number between 1 and 10 would be 4.56. We have to move our decimal over, okay? Now, if you're looking at that example, now, we moved that decimal over 1 spot. So that means we're gaining an exponent, okay? So, and where does the exponent go? It just gets added in to the exponent that the 10 already has. So we already have 10 to the 7. Well, we took that 45.6, we took that number, a number greater than 1, and we took a power of 10 from it, okay? We moved the decimal 1 spot. So that 10 is going to gain that exponent. That movement of the decimal went into the 10. All right, now, I'm going to leave us with that thought. I want you to think about that last example, and that is how we are going to start class tomorrow, okay? So we're going to end our video here, but to think about that next example, what might happen. We're going to finish up these notes at the beginning of class tomorrow.